Okay, we went through this in class, but it was pretty difficult for everybody to see what was happening. So I'm going to go through and do it one more time. It'll fill up the whole computer screen, so you'll be able to see what I'm doing really, really well. All right, so this is going from glaze formula to unity formula. Remember, for the unity formula, we're trying to get everything to add up to 1. Everything in the R2O, RO category. So the fluxes category, we want all those to add up to 1. And then everything is comparison from there. So you may hear in the background or see underneath the table my cat's going by, and just ignore them, or keep an eye out for them, whatever. Okay, so first thing I'm gonna do, write my name up here, glaze. We're gonna do the 4, 3, 2, 1 clear again. And we're gonna go to cone 10, date, whatever the date is, 719 is today. Okay, so this top part right here, we're not going to really use for this particular this thing. When we go back the other direction, that will be useful. So just ignore this top part. What we're going to do is we're going to do material. We're going to write the recipe down in this column. So I'll start out with Custer Feldspar. I'm going to skip 2 lines. I'm going to go silica or flint. When we get into the computer programs that do these things for us, we might need to use a different name for whatever we're doing. So I know the one program that I use, if I write silica, it doesn't recognize it, but if I write flint, it does recognize it. So whiting. Well, let's do EPK this time. Edgar Plastic Kaolin. So Custer is 40, silica is 30, whiting is 20, EPK is 10. Okay, cool. Now what we need to do is we need to figure out what materials we have. Oh, first let's do this, equivalent weight. We'll get to that in a second. I'll show you what that is. And then molecular equivalent. That's what that stands for. Okay, so these are going to be important things in a minute. Okay, so next I'm going to start writing down, I know that there's going to be potassium, I know that there's going to be sodium, and then to find out what all the other materials are going to be, I'm actually going to go into the lists of materials that we have. I actually discovered that there was a discrepancy in the OM4 that I didn't catch. The University of Utah one was updated in, I guess, 2012. And there must have been some sort of change, and the OM4 is a little bit different. So it doesn't necessarily matter 100%. If you want to go through and look it up on the Digital Fire reference, you can do that. As long as you're using the same thing to go one direction, you can use it to go the other direction, and you'll get the same effective results. If you use like one recipe, like if I were to use the one without the unaltered one, the unaltered unity formula for OM4 to go one direction, and then the updated one to go the other direction, then I'm going to have problems. So make sure that you're using just whatever you're using the same one to go both directions. Okay, so I have sodium, potassium, calcium, potassium, sodium, calcium, magnesium. let's see, I'm going to go to, so Custer feldspar is potassium, sodium, calcium. So those are the RO, R2O groups. So I can just go across here, potassium, sodium, calcium, magnesium. Just write those up top. Okay, now that's the RO, R2O group, fluxes. So now we're going to have the R2O3 group, and that's going to be Al2O3 and probably Fe2O3. If we're going to have boron, that would be B2O3, but we don't I know we don't have any boron in this particular formula, so I'm just going to, oh, this is not a very good eraser. Make sure you have a pencil with a decent eraser to start out with here. I don't think I have an eraser on anything here. They're all kind of crappy erasers. Okay, so never mind. So the R2O3 group, now we have the RO2 group, so so RO2, so I'm going to skip a column, SiO2, TiO2. So there's a bunch more columns. Maybe there's barium or strontium, or boron or something like that, or zinc. So we have a couple extra columns to add those things in if we need to. All right, so now we have all of the oxides that we are going to be using going across. Just you'll see it in the, if it's not completely obvious here, then, oh wait, I'm a dummy. I changed my mind. Okay, so I showed you the thing for Kentucky ball clay. We're using EPK, so I'm going to go back to that. Sorry to confuse you. Okay, so we're actually using EPK kaolin, which is potassium, calcium, magnesium. It actually doesn't have any sodium in it. So basically the same materials or minerals in there. Okay, so now what we need is we need the equivalent weight. So each material is going to have an equivalent weight. For the Custer feldspar, okay, we have 620.668. Okay, so that's our equivalent molecular weight. I'll write that here. Okay, and now from that we can derive the molecular equivalent, and I am recording on my phone, so I cannot use my calculator, but luckily I have my old one nearby. So if I divide 40 by 620.68, I'm going to get 0.064. Okay. Actually, hold on a second. I'm gonna find a calculator. Okay, so what I'm gonna do is I'm gonna go 40 divided by 620.68, and you get 0.064. If you want to like carry it out to a couple more decimal places to be super, if you want to be like really accurate about this, I mean as accurate as we can be with the materials that we have, then feel free to do so. Really, once we get to molecular, like the unity formula, we're going to only be 2 decimal places. Okay, so now what we're going to do is we're going to take the 0.064, and we're going to times that by all of these things in Custer feldspar. Now, one thing to note, in mine, Custer feldspar here is unitied to the RO, the R2O group, so the fluxing group. I have seen it where they're using it unitied to the Al2O3 group, That's fine as long as you're using the same one to go one direction and then back to the other direction. You'll be fine. It'll probably get you close enough anyway, but it's unity to this. So basically, this is the one unit, and then you have these other things that kind of go along, like these things that kind of go along with it. So you'll see what I'm saying about the one unit when we get to another material. Okay, so we're going to use these materials. So I'm just going to do 0.064, not the full decimal places. Okay, 0.042 for potassium times 0.64. Oops, 0.064. Make sure you have the proper amount of decimal places. 0.019. Okay, calcium is 0.033 times 0.064 is 0.002. Okay, there's no magnesium in Custer, so I'm not going to do that one. 1.043 times 0.064 is 0.067. Oops. Make sure you put it in the right column. I almost put it in the magnesium column. There's no magnesium in there. 0.006 times 0.064 is probably going to be negligible. It's 0.0003, which is beyond our like what I'm actually calculating. It's like too small to even bother, so I'm not even going to bother. 7.133 times 0.064 is 0.457. Okay, so this LOI, okay, right here, ignore that. That's loss on ignition. Basically, that means there's a particular amount of material that is volatile and will burn away when the kiln is fired. So just ignore that part. Okay, there's no titanium. We'll just skip that one. Okay, so silica and flint. Silica or flint. Now that we're going to move to this particular set of ceramic raw materials. I will put that online. Okay, so it's not, they don't call it flint here. Silica. Okay, so silica, flint, quartz. Great. So remember how I said in the unity formula for the feldspar, the fluxing oxides, so the fluxing oxides like this stuff, that will add up to 1, usually. As you see, this is a clay. The alumina actually is the 1 unit. Most of these other things are a single unit, okay? So there's just 1 SiO2 and 1 Na2O3 and 1 sodium nitrate, okay? Eventually you'll come to something with like talc, which is 3 magnesium, 4 silica, and 1 water, okay? And so whenever you run across those numbers, you have to times those numbers across. And maybe I'll do another one a little bit later on to show you what I'm talking about for that. But right now we have 1 silica, and that 1 silica's molecular and equivalent weight are both 60. So we're going to write 60 in the equivalent weight. And then we divide 30 by 60, and that's a pretty easy one. That's going to be 0.500. And now we have 1 silica, so 1 silica times 0.5. Make sure you put it in the right column. It's going to be 0.500 in the silica. Now there's nothing else in silica, so we don't have to do anything with that. Okay, whiting is calcium carbonate, but okay. Yeah, so calcium carbonate is whiting. Okay. The weight is 100. Okay. 20 divided by 100, what was that point? Oops. 2, yeah, that's what I thought. Okay, so 20 divided by 100 is 0.2. If there was more than one of each of the things in here, we could times it by whatever that is, but there's just one whiting. So calcium carbonate is 1, so we'll just times that to the calcium, 0.200, okay? Now EPK, so this will be a little bit different than the one that we did in class. Okay, so the molecular weight for EPK is 270.319. Okay, hard to fit 6 numbers in that. So 10 divided by 270.319. That gives us 0.037. I'm just going to round up. Okay, or it'd be 6. Well, it'd be 70 anyway because yeah, we'd be rounding that. Okay, now so that we need to times 0.037. Oh boy, I disturbed it. Okay, so 0.037 times all of these numbers here. Okay. Oh, there's one thing that I'm seeing. P2O5. P is phosphorus. Phosphorus is like one of the things that burns away, so we don't even we don't really need to pay attention to that. I'm gonna move this out of the screen while I get my calculator out. So 0.037 times 0.011 is 0.0004. That's beyond our reach there. And that's going to be beyond our reach. That's going to be beyond our reach. Okay. Unless you are actually going out to 4 decimal places, which by all means, you're welcome to do that. Alumina is 1, okay, times 0.037, that's just going to be 0.037. Okay. 0.009, that might actually do something, times 0.037. Nope, still 0.003. Let's see. Oh, I guess that's even less than those other ones. 2.098 is silica times 0.037 is 0.077, 0.078. Actually, we're going to round up. And then TiO2 is going to be negligible. So basically, one of the things that we're going for with the alumina, whenever we're calculating for clay, 9 times out of 10, we're using the clay to get our alumina in the formula. And so there's very little other stuff in there. There's alumina and silica and very little other stuff. So that's sort of where we sort of try to calculate that. Okay, so I'm going to draw a little line here, and we're going to add all this stuff up. So potassium is 0.042. Just going straight down the column here. Oops, looks like I moved out of the frame. So potassium going straight down the column is 0.042. Can you even see that? Yeah, you can. Sorry, the light is a little intense here in the middle of the page. Move off to the side there. Okay. Sodium 0.019. Calcium is 0.002 plus 0.200. 202. Magnesium is negligible. We really just nothing really came up with the magnesium. 0.067 plus 0.037 is 0.105. Actually, real math people would probably be putting 0 in front of everything. Okay, so silica has a few in the column here. 0.457 plus 0.5 plus 0.078. Oh shoot, I missed a number there. 0.457 plus 0.5 plus 0.078. Actually, probably would have been fine because I did 0.08 and it would have been just a rounded up 1.035, a rounded up version. Okay, so as you can see, like a lot of these materials, just because they're negligible, like you get to a point where you're just like, okay, well they're not really going to count for much of anything, so we'll just ignore those. If they fit within our range of decimal places, then we would definitely count them, but they were just too small. Okay, so now what we need to do is we need to add up the RO, the RO, R2O group. Okay, so total RO, can you see that what I'm writing? Yeah, okay. R2O, and that is 0.042 plus 0.019 plus 0.202 is 0.263. Okay, 0.263 is going to be our baseline. All right, so now what I'm going to do, now we need to take everything to unity. And the reason why I wanted the total RO, R2O group is so that I can divide everything else in, all the other oxides in this whole group together to, or sorry, divide them by that number to get our unity. Because the RO, R2O group is our basis, this will add up to 1 unless we really screwed it up. Okay, so we're just going to start out by doing potassium, K2O. Can we see that? Yeah, okay. Na2O, CaO. And if you look, there's no magnesium to speak of. I'm just not going to bother with that. I mean, I could have, but it probably wouldn't have given us really anything that would have counted for anything. So potassium is 0.042, sodium is 0.019, calcium is 0.202, and then we're going to divide that by our 0.263. That's going to equal okay. This one's going to be, you know what? I'm going to do, actually, it doesn't matter anyway. 0.160. 0.263. 0.072, 0.202 divided by 0.263 is 0.768. So regardless, so 0.6. Yeah, so if I rounded this up, well, regardless, this adds up to 1. Actually, it should, hopefully. So 0.768 plus 0.072 plus 0.16, and that will add up to 1. Now I'm going to do the alumina and iron. So alumina is pretty negligible. Or sorry, iron was pretty negligible. Alumina is 0.105 divided by our RO, R2O group, 0.263. Is 0.399. Okay, so when I did this with the OM4, it was a little higher than that. And the silica is 1.035 divided by 0.263 equals 3.935. Okay, so I'm just going to write out the unity so it's actually a little bit like easier to see. Like this, the way that this is written right now is pretty difficult to read. So I can actually do it here because I don't need quite as much space, I don't think. Maybe I'll do it down here. I'll do it down here. K2O. We'll just call that 0.16. Na2O. So sodium is 0.07, 0.07, and then calcium is 0.77. Okay, 0.77. Then we have the Al2O3, and that will be 0.40. And then we have the SiO2 as 3.94. And hopefully that looks something, yeah, it's a little less silica than the one with, a little less silica, a little bit more alumina than the one with OM4. So you can see that just a small change here. I'll even bring back the other one, and you can see I actually made a few mistakes. I had to like move some stuff around because I was a dummy and I put them in the wrong column. But you can actually see, oh shoot, I hope you can actually see what I was doing there. Here we go. So potassium, sodium, calcium is approximately the same. The alumina is 0.4, or it's 0.035 with the ball clay, and then 4 silica and 3.94 silica with the EPK. So 4 silica with the 3.94 with the EPK. So when you change the materials out, you can see that it is a little bit different, and it can change things. So now that we have that sort of baseline, we can sort of go from there and sort of extrapolate. I might, if I'm feeling ambitious, do another one with more complex materials where we're actually timesing by more than just one across. So we'll have to figure that out. Okay, that's it, and I hope that was a little bit easier to see than when I did it during class. Okay, thank you everybody.